Hey there, chemists. In this lesson, we're going to look at hybridization and how we use it to explain the bonding seen in organic compounds. I'm going to start by showing an animation from a publishing website. I believe this is from McGraw-Hill. I've just annotated it a little bit. This reminds us what atomic orbitals look like. There's carbon's atomic orbitals, 2s2, 2p2 in the valence. And this is what it looks like when it hybridizes. You get 4 new orbitals. This is an example of an sp3 hybridization from the mixing of the atomic orbitals. There's a carbon with its valence electrons by itself, but once it forms a bond, those valence electrons hybridize. So in this case, we're about to see a methane molecule, and the atomic orbitals merge to make what are called hybrid orbitals. And this is what we use to explain the tetrahedral geometry that we see in a methane molecule. Here's an ethylene molecule, also known as ethene. Ethene's got 2 carbons that are actually sp2 hybridized with each other. That goes hand in hand with the trigonal planar geometry. Now the carbons are bonded to each other with hybrid orbitals, but also with unhybridized orbitals. So here we have the same atomic orbital arrangement of carbon, 2s2, 2p2, but this time we're going to mix only 3 of the 4 and get 3 hybrid orbitals that are called sp2 orbitals. There's 1, 2, 3 electrons in them, and then 1 unhybridized p orbital that you see up there at a higher energy level. We go back to the model. Here's 2 carbon atoms, both unhybridized in the beginning, but once they come together to make a bond, they're going to hybridize, and we're going to see sp2 hybridizations from each one. So there's the sp2 hybrid model, and then 2 sp2 orbitals can overlap with each other. That's what happens when they form a bond. We make what's called a sigma bond. A sigma bond is from overlap that looks like that, when you have end-to-end overlap of the orbitals, in this case hybrid orbitals. And you can rotate around any sigma bond. We also have sigma bonds between hybrid orbitals and s orbitals, so those hydrogen atoms are eventually going to form bonds with the hybrid orbitals. Notice hydrogen is just in its spherical s orbital. There's no hybridization for hydrogen. The orbitals above and below the carbon atoms that you see now are forming a pi bond. That's from side-to-side overlap, and you cannot rotate around a pi bond. Those shaded regions are orbitals, and they just show the regions of most likely finding the electrons. And there you can see the sigma bond is stronger than the pi bond, but the pi bond is what prevents a double bond from rotating. And there's the complete model of an ethylene molecule with all the bonding shown. So let's go to our notes and take a look at what we just saw. So here's carbon's atomic orbitals. We're just going to look at the valence orbitals, the valence electrons in carbon's atomic orbitals, and what we'll see is that the atomic orbitals combine to form new hybrid orbitals. That's the key here. And we saw 2 of the 3 most common types in the animation just a moment ago. But here's the 3 that we're going to look at: sp3, sp2, and sp. The first one, an sp3 orbital, comes from combining all 4 of the valence orbitals, and you get 4 new hybrid orbitals. Because it's formed from a single s orbital and 3 p orbitals, we give it the name sp3. And all 4 of carbon's valence electrons end up in those orbitals, and they spread out 1 in each. So this is why carbon makes 4 symmetric bonds when it's sp3 hybridized, and you get that tetrahedral geometry that we're familiar with from last semester. The second common case we see is an sp2 hybridization. That's from combining 1 s orbital and 2 of the p orbitals. You get 3 hybrid orbitals. We call them sp2 orbitals. There's 1 electron in each. But then there's 1 unhybridized p orbital that's left over. Let me just slide all this text up higher to make some space. So here we have an unhybridized p orbital, also with 1 electron in it. And it's that p orbital in each carbon atom that's capable of making that pi bond. The pi bond is the second bond that we see in any double bond. So every double bond counts as a sigma from that end-to-end overlap, and then also a pi bond. But a single bond is just a sigma bond, and the pi bond comes from the overlap of p orbitals, always. The sigma bond is from the overlap of hybrid orbitals, as well as overlap of just s orbitals from things like hydrogen. So what about a triple bond? Well, since we started annotating it, let's go ahead and do that. A triple bond is a sigma bond, but then it's also two pi bonds. So in an sp hybridized system, we take one s orbital and only one p orbital to hybridize and get two new orbitals, which we call sp, each with one electron in it. And then there's two remaining p orbitals, each with one electron in them. So we can explain the bonding in even a simple molecule like acetylene, what's also called ethine, based on all these orbital rearrangements. The sp electrons in each carbon atom are making two sigma bonds, one each. One is happening with each other, and the other one is happening with the hydrogen that's attached linearly on the other side. And then those p electrons are forming pi bonds right there and right there. And there's a little blurb to the right of your notes that tells you about sigma and pi bonding and how the sigma is from head-on overlap and the pi bonding is from side-to-side overlap. So now let's actually draw how these orbitals look in space. How can we rearrange them and draw what happens? So for an sp3 system, we have an s orbital, which is spherical. And then we have three p orbitals, which I'm just going to draw as dumbbell shapes. We have one, let's call px, another py, and another pz. And these combine to give four new hybrid orbitals that are capable of forming sigma bonds. What does each individual orbital look like? They're not spherical or dumbbell shaped. They're kind of like a lopsided dumbbell. We often draw them like an asymmetric figure 8. Again, an orbital is just an explanation, a mathematical model of a region of space where you're most likely to find an electron. And then how does this look when they all combine around a carbon atom? It exists as a tetrahedral. So there's one orbital, there's another orbital, there's a third orbital, and then I'll draw back here the fourth orbital. And those are four sp3 hybrid orbitals symmetrically arranged around a central carbon atom, and you get this tetrahedral geometry that goes hand in hand with sp3 hybridization. And don't forget there's also a bond angle that we learned last semester, 109.5 degrees. So what does it look like for the sp2 system? Let's do that. You still have the same starting point. You still have one s orbital and three p orbitals. So I'm just going to copy that. That's the same for this. In fact, that's the same for the sp hybrid system as well. But it's going to combine differently than what we just saw. Let's do the sp2 system. The sp2 system is going to leave one of those p orbitals unhybridized. And then you have three hybrid orbitals. They actually look the same in terms of their shape as an sp3. It's still just a hybrid orbital, but these are sp2 orbitals. We give them a different name. What does it look like when they're arranged around a single carbon atom? Well, you have a single carbon atom now with three symmetrically arranged hybrid orbitals in a trig planar geometry, and then one unhybridized p orbital. So we have our p orbital, and then three sp2 hybrid orbitals, all capable of forming sigma bonds. This is a trigonal planar arrangement, and you should remember that between those hybrid orbitals, you have a 120 degree bond angle. So I'd like you to hit pause and see if you can figure out what you might draw as a picture for the SP system. What's the last one going to look like? And see if you can remember what geometry and bond angle goes with it as well. Okay, in the SP system, you're going to have two unhybridized p orbitals left alone, and two hybrid orbitals. And if you guessed that they look the same as the other hybrid orbitals, you are right. And then when you arrange them around a carbon atom, we get two hybrid orbitals arranged linearly, and then also two unhybridized p orbitals. There's one, and then a second one, this is getting very crowded, perpendicular to the first one. There's an sp orbital, there's an sp orbital, and then we have a p orbital and another p orbital. This is arranged in a linear geometry, and hopefully you remember that the bond angle between the sigma bonds is 180 degrees. So those are the three most common hybridized systems that we see in organic compounds, and a little bit more of a pictorial diagram of how they're arranged around each individual atom. Let's just wrap up by summarizing what we saw with sigma and pi bonding. In a sigma bond, electron density lies along the line connecting the atoms. That's what's called a sigma bond. And I have pictures here that show this. This occurs anytime you have s orbitals overlapping with each other or any hybrid orbitals overlapping with each other. So all of these are examples of sigma bonds. This is as opposed to a pi bond. When electron density lies above and below the line and they connect along the edge, that's called a pi bond. And that's only between p orbitals, unhybridized p orbitals. The pi bond is weaker than the sigma bond, but obviously the sum of the two is stronger than any one individual. And then what you really need to know when you're looking at a structure is that a single bond is a sigma bond. But a double bond is one of each. That's a sigma and a pi. And a triple is one sigma and two pi bonds. So the strength of the bond increases from single to double to triple, but it gets easier to break those pi bonds compared to a sigma bond. A pi bond by itself is weaker than a sigma, but the sum of them is stronger than any one by itself. And that's a review of how we look at bonding in organic compounds.